There we go. All right. So anyway, I was been mentioning that today's the last day for those of you who just came in. Today's the last day for our Zoom meetings. Um, and then what's going to happen starting on Wednesday, there will be pre-recorded videos. There's 4 of them. So there's 1 for this Wednesday. There's 2 next week, Tuesday and Thursday, excuse me, Monday and Wednesday. As I was saying, I would recommend that you would watch them on the normal time that you have for this class. You might as well watch them at that time. And then the week after that, on Monday the 29th, there's a pre-recorded video on that one too. Now, all those pre-recorded videos are for chapter 6, both on confidence intervals and hypothesis tests, where everything is fully developed. I would recommend trying the homework. And if you're having difficulties with the homework, make sure that you only do 2 attempts out of the 3, and just wait till I come back to try that 3rd attempt if you're having any difficulties. Because if you try all 3 attempts, then you won't be able to go back and answer those questions. So now, I did change all the due dates. So all the due dates for chapter 4 and so forth, I think it was yesterday. I changed all the due dates, so it's easier for all of you to finish your homework. Unless I made it next Sunday, I'm not really sure, but I gave you enough time. Any questions about anything of how everything's laid out? When I get back on December 1st, we're going to have a review on confidence intervals. So I'll show you everything you need to know about confidence intervals for both the test and for the final exam. And then I'll also give you some detail about how to do everything in Excel, so you can do your project. All right, because Excel is not going to be that hard. It'll be very straightforward to do both confidence intervals and hypothesis tests, because there's very specific functions for those things. So, but you have to know the actual functions. And then, so Wednesday the 1st, December 1st, is when I do a review on confidence intervals, and then the following Monday, I guess, what is that date? That would be the 6th, I guess, December the 6th, will be the review for hypothesis tests. So make sure that you're available for those reviews. The test is going to be that Wednesday, December the 8th. All right. Now I'm going to make the tests very straightforward because I know that some of you have difficulty studying in this format online as opposed to doing it in class. So I'm aware of that, and the test will be more straightforward than my normal tests. It'll be based basically on the review. So whatever I do in the review, something similar will show up on the test. All right, so no surprises, nothing unusual. And you just have to do all the homework, watch the videos, and then you should do okay. You should be fine. All right, so I'm aware of everything. I'm aware of how most people study and so forth, so don't worry. So today we're going to cover 5.1, again, hypothesis tests. And so let me share with you. Let's see if I have it open. Just give me 1 second here. Okay. All right, so give me a thumbs up if you see the textbook, okay? Yes, good, thank you. All right, so let me get some of these boxes out of the way. All right, so let's scroll up to the beginning of this section, 5.1. Now, 5.1, by the way, has a review of the normal distribution at the beginning, which we've already covered, but it's a nice review. The whole idea here is that when we're using StatKey to do these randomization hypothesis tests, many of the graphs that we show that are indicated in Stackey look like a normal curve. They look bell-shaped. So the whole idea in this section is that, yeah, why don't we just use the normal distribution as an approximation to do hypothesis tests. In other words, to create our test statistic. And I'll go through the steps again. This will become clear, by the way, during the videos. When we actually go through the videos on hypothesis tests, the pre-recorded videos, I will show you the 6 steps of doing a hypothesis test. So that's why the videos are important. And I do plenty of examples. So in the videos, you'll see exactly what I'm doing and also using the calculator. Now, we're not quite there yet, but we're going to start using the calculator today. But anyway, in the beginning here, they're showing you, giving you an introduction to normal distribution. Once again, we saw this in, I believe, section P5, I believe, or P4, I forget which one it was, on normal distributions. All right, so we've covered this in part 2 of the course, but this is a nice review. Tells you the standard normal and shows you how to find areas. We already know how to do this with our calculator. Even shows the formula for converting an X, the normal, any normal distribution, into a Z, which is a standard normal using this Z-score formula. So we've already covered all of that. All right, so this has all these examples. Also mentions this thing called the central limit theorem, which says the following. It says that regardless of the population's distribution's shape, in other words, if we look at a parameter like a mean or a proportion, it says basically that no matter what the shape of the population distribution, whether it's skewed or symmetric, if the sample size is large enough, that is, well, if it's large enough, then the sampling distributions, the sampling distribution, remember, is a list of all possible samples of a certain size. The sampling distribution will be normal if the sample size is large enough. So if we were doing a hypothesis test for a mean, we're looking to see if the sample size is 30 or bigger. All right, so if there's no information about the population, if we don't know whether it's normal or not, or if we're specifically told that the population is skewed left or skewed right, then we need a sample size for a sample of at least 30. Now, it doesn't say it in this book, but it says in pretty much every textbook. That's sort of a rule of thumb, 30. Do remember, however, that if we were doing a hypothesis test for a proportion, it's a little bit different to determine whether we can use the normal distribution for our sampling distribution. And maybe you remember this. We calculate n times p and n times 1 minus p. Again, this is for proportions, where p is the proportion. And we want to see if those two calculations are at least 10. If they are, then we can use the normal distribution when we are doing a hypothesis test for a proportion. Okay, but again, I'm going to review all of that in the recordings. Okay, and also when I get back, when we do our reviews, I'll show you the 6 steps of hypothesis test. So there is the 6 steps. I'll sort of mention it today, but I will go through all of that more when I get back. All right. So that's the central limit theorem. It's an important theorem of statistics. And we're going to start doing some examples here of hypothesis tests. And we're going to do this one first, okay? And what I'm going to do is I'll show you the problem, and then we'll go into Stackey and actually replicate this and do a hypothesis test. And I'll show you, in general, what we're doing, all right? So let's read through this problem here. It's called Eating Organic. And it says many people pay more to eat organic when possible, but the question is, but does eating organic food actually offer health benefits? All right. So spurred on by her parents debating this question, a 16-year-old girl decided to investigate it with a science project. She randomly divided fruit flies into 2 groups and fed one group conventional food, all right, and the other group, the same type of food, but an organic version of it, all right? So one group got conventional food that was not organic, and the other group got the organic version of the same food. And you can see this, right? You go to a place like Whole Foods or someplace like that, they have an organic section, and then where the vegetables are, and then they have the regular vegetables, all right? So you sort of understand what they're saying. She then followed the flies and measured variables like longevity, fertility, and other things. Her results earned her honors in a science competition, blah, 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 and she was published. Here we're examining the survival of fruit flies eating potatoes. All right, so this is one of the specific things she was looking at. And she says after 13 days, 318 of the 500 flies that were fed organic potatoes were still alive. So they had survived. All right, so how many fruit flies were there who were in the organic group? Well, if we call the organic group group 1, there was 500 of those flies. And the number that survived is 318. Okay, so that's information you would write down. Now, one of the things I recommended to some students that I've met with over Zoom who requested meetings is that you have a pad of paper and a pen next to you. And when you're going through these problems, write down the data so that you can't, because what many students do with these types of things, they read through it and they're sort of trying to understand it. And then they start, and they don't write anything down. And then they start looking at the question, and then they have to go back and read it again, and maybe 3 or 4 times they have to read it. Instead of doing all of that, you need to pick out the data that's being given, and then determine what you need to do to actually answer the question, all right? So what I would do is I would call group 1 the organic group, and I would write down their sample size, 500 flies. That would be N1. I would call it N1 as the sample, that's the group 1 sample size. And then 318 are the number that are still alive. Now, obviously, this is sort of like a binomial, right? Because if 318 are still alive, then the remaining of the 500 died, right? That's sort of what they're saying here. 318 lived after 13 days, and the remaining, I guess, which is 182 of them, died. Now, for the group 2, which is the flies that ate the conventional potatoes, there were 500 of those flies, and only 285 of those survived. So fewer of those survived. All right. Now, we want to see if eating organic potatoes actually increases. So let's actually read it down here. It says define P0 and PC. So P0 would be the organic group. That's what they're saying, the proportion eating organic. So that's the group 1. And then group 2 would be PC representing conventional potatoes. All right, so that's the notation they're using. And it says here, we're interested in whether the proportion of flies alive is higher for the flies that eat organic than for the flies that don't eat organic. So this is the null and alternative hypothesis. Now, remember, the 500 flies for each group were just randomly selected, right? They're sort of we're assuming that 500 were randomly selected fruit flies. And there could be thousands of these flies, right? So we're not going to be measuring how long all the flies are alive. So we're taking a random sample of 500 for each group. Okay. Now, the actual sample statistics are listed down here. Now, notice that we're interested in the difference between the organic group's proportion and the conventional group's proportion. And this is the sample version of it, right? This is sample. And notice it's for the organic group, the proportion is 318 divided by 500. And for the conventional group, 285 over 500. We subtract their proportions, we get 0.066. So that's the difference in proportions for that one sample, 1,000 flies, 500 eating organic, and 500 to a conventional, right? So actually what I'm going to do is I'll go into Stackey now. Stop sharing, and I want to show you, let's see if Stackey is open. That's not open, so let me second. All right, where is Stackey? Here it is. All right, so let's find the Stackey. All right, here we go. So I'm going to actually go back, and this is this problem is a difference in proportions. All right, so we're going to go to the randomization hypothesis tests. Again, I am not going to test you on this, but the homework does have these randomization tests in it. So if you wanted to go in here and play, you can go in here and play, just so that you understand what they're doing in the homework. But anyway, I'm going to, and I think having Stackey available is important to actually do the homework. All right, so I'm going to choose the one for the fruit flies, and it's all the way down to the bottom. Here it says alive flies, organic potatoes. All right, that's the one. You can see over here on the right side is the original data set. Okay, again, the organic group, non-organic. Organic group's group 1, and non-organic, not organic group is group 2. You can see the data here, the count and the sample size. Here are the proportions, and here's the difference in proportion between the two groups. All right, now the null hypothesis would be there's no difference between the two groups. And the alternative is that P1, which is the organic group, is going to be bigger than P2, the non-organic group. That's what they want you to test, to see if eating organic actually improves the life expectancy of these fruit flies. So since it's a greater than problem, remember the alternative hypothesis determines whether we have a left tail test, a right tail test, or a two tail test. Since the alternative hypothesis has a greater than symbol, we're going to do a right tail test. And I'm going to generate 1,000 of these. Now, notice here that they put the 0.066, the sample proportion. It doesn't always work out this way, by the way. It just happens to work out here that 0.066 down here matches the sample proportion. Typically, you have to click here and type in the difference in the proportions. But in this case, it's already there. So since it's already there, the 0.025 is our p-value, the p-value, if you remember that. Now, in this particular case, this is how we did it in chapter 4, all right, when we did our hypothesis tests. We strictly worked with this particular chart. Now, here's the deal. The deal is that we're going to wean ourselves off of these charts here. This is just to illustrate how to find p-values, right? Using this, and we're going to start using formulas. All right, so this chapter here, we're going to start, instead of finding the p-value this way, we're going to use a formula to find what's called the test statistic. All right, the test statistic. Now, the only thing that we're going to pull off of this chart here is going to be the standard error. This up here in the upper right-hand corner here, we're going to use the standard error 0.032. All right, 0.032. At least that's the standard error that I'm getting when I'm running this randomization test. All right, remember, this is simulation. It's not real. It's using the original data, but it's not. These dots here represent what are called randomization samples of size 1,000. All right, this is one example down here of one of these 1,000 dots. All right, but they're not real samples, necessarily real samples. Okay, so we're going to do the same thing, and we're going to see if we can come up with, and we're going to start using formulas, and let's see we get it. Let's see if we get a p-value close to this 0.025. All right, so let's go back to the problem. And we'll go back to the book. So, unfortunately, the Zoom only can keep certain, if I have like 6 or 7 of these screens open, and I have to switch over for you to see it under sharing. So just give me a second. Let me actually share this. And then I'll show you how we do this. Now, notice when they did it in the book, and actually we'll just use the book's data here. This is the same plot, the similar plot to what I just did in StatKey. And notice, first of all, notice that the p-value came out to 0.015. It's a little bit different because this is a different randomization distribution than the one I just did in StatKey. The standard error, however, the 0.03 here is going to be pretty similar to what I did, all right? Notice the null here is 0, because the way the randomization distribution is created is that it assumes that the null hypothesis is true. So the null hypothesis says there's no difference between the two groups, the two proportions. So the difference between the two proportions will be 0 as the null hypothesis. So that's why it's in the middle here. And here's the 0.066. This is the difference in the two proportions for that one sample that we were looking at. All right. Now the question, of course, is, are we going to, with this p-value here, are we going to reject or not reject the null hypothesis? So first of all, let's see if we can calculate the p-value as if that curve that we just saw is a normal curve, all right? So here's the randomization plot again, and look what they're doing here. They're drawing a normal curve around it because it looks kind of normal. So they're saying, let's assume that we're going to use this normal curve instead of the randomization plot. And we're going to assume that this is a normal distribution with a mean of 0, because the null is 0. And the standard deviation we're going to use is what's up here, 0.03. All right, so we're just going to do what's in the book here. So we're going to assume that's our normal distribution, right? With a mean of 0, standard deviation of 0.03. Notice that's what they're using right here. Okay. All right. So question, what we're going to do next is, how do we find that p-value? Well, the very first thing we're going to do is we're going to create this test statistic. Now, this is what's going to be different from what we did in the past. Now, I sort of showed you this formula before. It's a z. Notice the numerator is the sample statistic minus the null parameter. Now, what exactly is that? Well, the sample statistic in this case would be the difference in the two proportions for the sample. That's the 0.066. All right? That's our the difference in the sample proportions. That one sample that we're looking at. And then it says minus null parameter. What's the null parameter? Well, that's the null hypothesis. That's the value of the null hypothesis. And the null hypothesis says that the two proportions are equal, which means the difference is 0. So the null parameter is 0. So the sample statistic in this case is going to be 0.066, and the null difference is 0. That's our numerator. The denominator of this test statistic, SE, is, we're reading it right off the StatKey chart. And remember, in the book, it's 0.03. All right? So let's look at, this is exactly what they're doing here. You can see here, the sample statistic, again, 0.066. The null parameter is 0. And the standard error, they're in this case, we're just reading it right off of the stack key chart. And when we divide these two numbers, we get 2.2. Now, what is this 2.2? It is the z-score that we're going to use for a standard normal curve. All right, the z-score, 2.2. So here's a standard normal curve with a mean of 0, standard deviation of 1, and here is 2.2. All right. Now notice here that they have 0.014. Let's find this 0.014 using our calculator. Because we have a standard normal now with a mean of 0, standard deviation 1, and our z is 2.2, and we need to find the area. So if we know the z-score, z-score, we can find the area. Now, why are we looking at the area to the right of it? And that's because the alternative hypothesis is a right-tailed test. It says greater than. When it's greater than, we're using the right tail. So that means we're going to find the area to the right. All right. So what we're going to do now is go to our calculator, and we know the test statistic. And actually, what I'm going to do is I'm going to show you step by step how to do this using your calculator. All right. Actually go all the way through and calculate our p-value, and then and that's it. We'll look at the p-value, and then we're going to compare that p-value to what's called the level of significance. I believe that was mentioned in chapter 4. All right, let's go ahead and do that. So just give me a second here, and calculator all ready to go. Second. Okay. Again, yell out if there's some difficulties with seeing things, whatever, because sometimes I forget to do the sharing. All right, so hopefully you'll see the calculator now. Now, let's actually calculate. First of all, calculate our test statistic using our calculator. Right, it was done in the book, but let's actually use the calculator. So I'm going to actually open up a set of parentheses. And we know that the sample statistic, the difference in proportions, is 0.066. We know that our null difference in proportions is 0. We'll close the parentheses, and we're going to divide that by 0.03, which is our standard error. Here's our 2.2. Now, what I would normally recommend to you is, because this is really easy, 2.2, we can remember it, but it would be good if you got into the habit when we do all of this, is that we could step by step calculate our p-value. And the way to do this, the easiest way to do it, is just to store the test statistic. In this case, it's unnecessary, but you can store it. And the way to do that is to hit the store button, and then do alpha, and we'll put it in letter A, alpha A, and hit enter. And now that 2.2 is stored in alpha A. And I think if you do this for any of the problems, store the test statistic, because sometimes you're going to have a test statistic that has many decimals in it. So instead of rounding it, you can basically store it, just like the way I just did. Now, to find the p-value, what we're going to do is we're going to, in this case, we're going to do a normal CDF. Normal CDF is what, sorry, one. There we go. Scroll down to normal CDF. Now remember, those with the 83 calculators, you'll have an open parentheses, and then you have to put these 4 numbers in with commas in between. Now remember, when we're finding an area to the right, The lower endpoint will be that, in this case, that would be that 2.2, but we know we stored it in alpha A. So we can simply just type in alpha A here, and that's our lower endpoint, because that's what the number is. Remember, this is a right tail that we're looking at, finding the area to the right tail. The upper, again, we'll use 1,000. Again, that's just arbitrary number, a big enough number to the right. And since this is a standard normal, we keep the mean and standard deviation as 0.1. You hit enter and hit enter again. So the area to the right of that test statistic is our p-value. And notice it is 0.0139. That is our p-value, 0.0139. Okay? So notice that we did not use StatKey to find the p-value. We're actually using a formula to find the test statistic and then plotting that test statistic on a standard normal curve and finding, in this case, the area to the right of that test statistic, and that gives us the p-value, 0.0139. Okay? Any questions about that, what I just did? Okay. All right. And again, the homework, when you go through the homework, they're going to give you plenty of practice doing this. So what we just found was the p-value using our calculator as opposed to using StatKey. All right, so we'll stop sharing here. And let's go back to the book. Okay. Notice they have 0.014. Pretty close, isn't it? So 0.0139 rounded to the 3 decimal points gives us the same answer. All right. So this time we used a formula as opposed to StatKey. All right. And why do we use the formula? Because we're assuming a normal distribution for our sampling distribution. Right. Now, one of the two assumptions, and again, you'll see this more and more when I start posting, when I will post all of the information about doing all these hypothesis tests. Well, let's see, what was I going to say here? The assumptions, yes. The first assumption is, and these assumptions have to be met, is that the samples would have to be selected randomly. That's always an assumption. And number two, the assumption here is the sample size is at least 30. Well, it certainly is, isn't it? All right, we have 500 flies for each of the two populations. So it's definitely the sample size was met. The criteria was met, and also the samples were randomly selected. That has to be true also. All right. So the test statistic. So the very first step in a hypothesis test is to state the null and alternative hypothesis correctly with symbols. The second step is the assumptions. The third step is the test statistic, which we calculated to 2.2. The step number 4 was calculating the p-value. We just did that, 0.0139. And then this fourth step would be comparing it to what's called the level of significance, which we went over before, right? I believe we went over it in chapter 4. The level of significance, the alpha, all right? We compare, and when the p-value is less than alpha, we reject the null hypothesis. Now, if alpha in this case was 5%, 0.0139 is less than 0.05, and therefore we would reject the null hypothesis. And that would support the claim in this case here that the organic group, a greater proportion of the flies survive if they eat organic potatoes as opposed to not eating organic potatoes. Okay, that's sort of what this would assume. Now, if we made had we made the alpha to be 0.01, we would come up with the opposite conclusion because 0.0139 is greater than 0.01. So at the 1% significance level, we would not reject the null hypothesis. All right. So that's how, that's a decision based on what alpha is. We have to see if it's less than alpha or greater than or equal to alpha. Any questions about that? All right, because here in the book, they're just looking at how to calculate the p-value. What I'm doing is basically comparing it to alpha. All right. That would be step number 5. And then we would do an interpretation, which is step number 6. Again, the 6 steps will become clear when we do chapter 6, because I go through all of that. Chapter 6 here, we're basically introducing how to calculate the p-value using a formula instead of using stack. Here's another example. This has to do with body temperature, right? Normally, body temperature for a human is 98.6, the inner core body temperature. And the alternative hypothesis in this case is that do people in general have a different body temperature? So it's not really 98.6, it's something different. It's either less than 98.6 or it's greater than 98.6. So the alternative hypothesis is just determining whether there is a difference, whether it's just, in general, the population just has a different body temperature other than 98.6. All right, so once again, what they're going to do here is they'll run this through StatKey, and they come up with a standard. You do that, at least from the book, if you did it through StatKey. This would, of course, would be a randomization test for a single mean. And actually, maybe we should do it. Just show it to you really quickly. All right, so let's go ahead and do that. Go back to StatKey. All right, so, and actually, all right, hold on one second. I have to actually show this to you guys. All right, just hold on one second. I apologize. This Zoom sometimes it ends up working kind of in a funny way. All right, so this will be a test for a single mean. And actually, they do have the body temperature here. Notice there were 50 people selected for this particular study. And the average for the 50 people was 98.26. That was the average temperature. Now, in this case, we just wanted to see if the alternative hypothesis is that the mean body temperature for the population as a whole is something different than 98.6. This is going to be a two-tailed test. Run 1,000 samples of this. So the word different tells you it's two tails. Then down here, if we were going to do this p-value thing strictly with using the StatKey, we would put 98.26 here. All right, and whoa, this did not come out correctly. Let me do it again. 8.26. Apologize for that. More time. 98.26. All right, it's not working very well. So I'm going to actually, let's just look at the standard error. It says 0.106. This is probably why you don't want to use StatKey, because StatKey sometimes doesn't work well. We're going to do this through a formula. Let's go back to the book. There we go. All right. Now, the standard error we picked off the chart, according to this, is 0.1066. And notice the mean is that 98.6. That's, we're assuming that's the null hypothesis, that it's equal, the mean is equal to 98.6. We're going to put that in. And we're going to assume a normal curve around this randomization curve. And the standard deviation is 0.1066. So the mean is 98.6 and standard deviation 0.1066. All right, so we read that standard error off the curve. And then notice here, this is the z-score. This is the z statistic. All right, the z statistic. So the numerator is the sample mean, 98.26, minus the null mean, which is 98.6, and the denominator is the standard error, 0.1066. And they came out with negative 3.19. So we did this with the calculator before. And actually, let's do it. Let's just do it with the calculator one more time. All right, so this is going to be a two-tailed test because the alternative hypothesis says not equal to. So the test statistic, open up a set of parentheses, it's going to be, what was it again? 98.2, was that it? Can somebody yell out what it was, what we said? It was 98.26, is that it, or 98.2?
Yeah, that's correct.
Which one was it, 98.26?
Yeah.
All right, so say 98.26 minus 98.6. And we're going to divide that by the standard error, which we're reading right off the stat key, is oops, sorry about that. We have to do this again. 98.26 minus 98.6. And we're going to divide by 0.1066. So that is our test statistic, our z test statistic, and we're going to store it. Notice all the decimals there. We're not going to round it. We're going to store it in alpha A. All right, now this is a two-tailed test. When we calculate the p-value, it's important that we multiply by 2. So notice it's a negative test statistic, a negative z, which is going to be to the left of 0, right? The mean of a standard normal is 0, and our z-score is a negative number. So the area that we're going to find is to the left of that number because it's a left tail, because it's negative. However, because it's a two-tailed test, whatever area we find using normal CDF, we have to multiply by 2. So I'm going to multiply by 2 first, 2 times, and then we're going to do normal CDF. Normal CDF. Now, it's the area to the left. Remember, the lower end is going to be negative 1,000, right? Because it's a left tail. And upper end is going to be what we stored in A, all right, which in this case would be that negative 3 point, whatever the number was. See, I don't even remember anymore, but it doesn't matter because I stored it in A. All right, that's why storing is important, because if you don't write things down, you might have forgotten. So anyway, you scroll down. This is a standard normal. We're just finding the area to the left, and then we're going to multiply by 2. You can see the 2 times the normal CDF. Again, I have to tell you that the only reason I'm multiplying by 2 is because it's a two-tailed test. And why do we know it's two-tailed? Because the alternative hypothesis says not equal to 98.6. The mean is not equal to 98.6. We're going to hit enter. And that is our total p-value, 0.0014. Okay? rounding that to 4 decimal places. That is the p-value. And so we're doing this through, again, we're calculating a test statistic, we're plotting it on the standard normal curve, we're finding the area, and in this case, multiplying by 2 because it's a two-tailed test, and it gives us our p-value. All right. Now let's go back to the book. And notice it exactly, it's an exact match to what they show in the book. 0.0014 is the p-value. Now that's a very low p-value, which indicates, so if the, let's say the alpha level of significance is 0.05, that's much smaller than alpha. And when the p-value is smaller than alpha, we reject the null hypothesis. So this particular sample actually provides evidence that in general the core temperature is not 98.6 for the population. It's something else other than 98.6. So if the alpha was at 5%, we would say something like, at the 5% significance level, there is not enough evidence to support. There is enough evidence to support the claim that the core temperature of the population is something other than 98.6. Okay, so that would be the conclusion, rejecting the null hypothesis. Any questions about how we're using a formula to come up with this? Any questions? All right, and this is another example here where we're looking at National Football League games. Okay, and so this is in 2018. There were 256 games played, and the home team won 153 of them. So remember, this is just one season. The National Football League's been around many seasons in the past. It will have many seasons in the future. This is just a sample of 256 games. All right, I don't know if it's a random sample, we can assume randomly selected. Anyway, 153 of those 256, it says the home team won as opposed to the visiting team. All right, so the 153 divided by 256 is the sample proportion, 2018. And they want to know if, in general, whether the home team wins more than half of their games in the NFL for the whole, whole population of all NFL games. Can we state that the home team wins more than half the games? All right. So we're assuming some sort of home field advantage for the home team. So what is the alternative hypothesis? Is that the proportion of games won will be greater than a half, greater than 0.5. Doesn't that make sense? When you see they win more than half the time, that means the alternative hypothesis is P is greater than 0.5. So that's a right-tailed test, isn't it? Now the null is going to be P is equal to 0.5. They win a half their games. So there's no home field advantage. That's the null hypothesis. Look at the test statistics. It's 0.598 is the sample statistic. That is, of course, 153 divided by 256. That's the 0.598. When you divide those two numbers, you subtract the null, divide by, where do they get the 0.031? If you go into StatKey and you run about 1,000 of these randomization samples, that's what the book came up with as the standard error for all those samples. Notice the test statistic is 3.161. And then when we calculate using the normal CDF, and this is a right-tailed test, using normal CDF, we came up with a p-value which is really small. So again, this supports the idea that the home teams win more than half their games. Okay. All right. Any questions? All right, so let's actually do a couple more of these things, and then we'll call it a day. I do want to mention a couple things about homework in chapter 4. So we'll go through these, and then we'll spend about 2 minutes. I'll spend about 2 minutes showing you some homework from chapter 4, so that you know how to answer the question. Somebody brought this to my attention. I was reviewing homework. All right, so let's look at 5.23. This is the one now. I'm purposely selecting the odd number one so that when you review, you can actually, here you can see what the solution is. All right, they'll go through the solution here in the ebook. Right, and there's actually a, sometimes they have these videos that all right, anyway, 5.23, it says cognitive science consistently shows that one of the most effective studying tools is to self-test. There's a recent study reinforces finding. In the study, 118 college students studied 48 pairs of Swahili and English words. All right, don't worry about all the details here, but you know, first thing I'm going to write down is the sample size is 118. This is a sample of 118 college students. So I'm writing that number down. All students had an initial study time and then 3 blocks of practice time. All right. During the practice time, half the students studied the words by reading them side by side, while the other half gave themselves quizzes in which they were shown one word and had to recall its partner. So students were randomly assigned to 2 groups, and total practice time was the same for both groups. All right. So half the students studied the words by reading them side by side. The other half gave themselves quizzes. All right. So that's the self-testing group. On the final test 1 week later, the proportion of items correctly recalled was 15% for the reading study group and 42% for the self-quiz group. A big difference in the amount recalled, percentage recalled. This the standard error for the differences in proportions is 0.07. Okay, so the first group, the group 1 is going to be the self-quiz group. So p hat, the sample proportion for that group is 0.42, it's 42%. And for the group that just did reading, studying, the regular way of doing it, that group 2 is 0.15 is their proportion. Standard error that we're going to use is 0.07. Test whether giving self-quizzes is more effective and show all details. So the difference in proportions of the null hypothesis is that P, we would write P1 minus P2 is equal to 0. There's no difference between the 2 groups. And the alternative hypothesis would be P1 minus P2 is greater than 0. There is a difference between the 2 groups. Okay, everybody clear on that? So P1, another way of writing is P1 is greater than P2. We could write it that way. So P1 is equal to P2 in null. The alternative would be P1 is greater than P2. And again, group 1 is going to be our self-testing. All right, so let's go to our calculator and actually calculate the p-value. We're going to have to calculate our test statistic first. All right, so let's stop sharing. Let's get our calculator. Show you step by step how to do this. So we calculate our test statistic first. The numerator of the test statistic is going to be our sample difference in proportions. Now remember, now what we can do here, by the way, is instead of calculating it, we can let the calculator do it. So I'm actually going to put in another little set of parentheses inside here. I'm going to put our sample statistic as 0.42 minus, because it's the difference in proportions, minus 0.15. All right, a little lazy. That's what I'm going to write in. So that's 0.42 minus 0.15 is the sample difference in proportions. And then the null difference in proportions is going to be 0. And what are we going to divide that by? The standard error, which in the problem they said is 0.07. So that's our test statistic. 3.857. I'm going to store it in A, alpha A. All right. Now, this is a right tail test because we want to see if group 1 is bigger than, we want to see if there's a, if the self-test group is, which is group 1, has a bigger proportion that retain the words than the other group. So it's a greater than problem, a right tail test. So since it's right tail, we don't have to multiply by 2. We're just going to know it's a right tail. And since it's right tail, we put our A as the lower, as we put our test statistic as the lower end of the interval. So that's what we're going to type in alpha A. We already stored it in A, the test statistic. 1,000, positive 1,000 is the upper end. There. All right, that's our p-value. Look how small this is. Remember that e-5 at the end means 10 to the -5 power. So this is 5.738 times 10 to the -5 power. All right. Somebody's telling in. And that means if we move the decimal point to the left by 5, so we get 4 zeros, 0.000 and 574 maybe. Basically, this is a very small number. And so our p-value is really small, 0.0000574. And again, if alpha is, again, something like 0.05, 5% level of significance, we're going to reject the null hypothesis. So since we're rejecting the null hypothesis, we would say something like there's enough at the 5% significance level, there's enough evidence to support that self-testing improves retention, something like that. Okay, so that is how we calculate the p-value. Any questions about that, for that problem? All right. We're also going to look at one more, another one quickly, and share the screen here. All right, the next one is 5.25. Let's look at that one. So this one, the one that it's 5.23, that is a right tail test. 5.25 says dogs ignore an unreliable person. A study investigated whether dogs change their behavior depending on whether a person displays reliable or unreliable behavior. Dogs were given 2 containers, one empty and one containing a dog biscuit. Experimenter pointed to one of the 2 containers. If the experimenter pointed to the container with a treat on the first trial, 16 of the 29 dogs followed the experimenter's cue. All right. However, if the experimenter misled the dog on the first trial, only 7 of the dogs followed the cue on the second trial. Right. So there's the group. The first group has to do with the experimenter pointing to the container with the treat on the first trial, and then it says on the second trial the dogs kind of learned something, right? They learned that where the treat usually is. If you have a dog, you'd kind of know this, right? So 16 out of the 26 of them actually followed what the experimenter did on the first one. And then on the second, that's group 1, and then group 2 is if the experimenter misled the dog on the first trial, only 7 of the 26 picked the one with the dog biscuit. All right. Okay. So 16 out of 26 for the first group, 7 out of 26 for the second group. Those are the 2 proportions. Test to see if the proportion following the cue is different, depending on whether the person exhibit reliable or unreliable behavior. So this is a difference in proportions question. That the alternative hypothesis says that there's no difference between the 2. Excuse me, there's a difference between the 2 groups. That means not equal. So you would say something like the proportion for group 1, the reliable group, is different or not equal to the proportion for the unreliable group. right? So it would be not equal to in the alternative hypothesis. The null hypothesis, there's no difference. It says use the 5% significance level. And by the way, they said the standard error is 0.138. 0.138 is our standard error. Okay. Let's actually go to our calculator. And let's run this really quickly. Once you get used to this, you'll be able to know the steps pretty quickly. The first thing is the test statistic. Now, we have fractions here instead of whole numbers. So we have to be careful how we do this. So the test statistic is going to be 16 divided by 26 minus 7 divided by 26. So how do we want to do this? So the way I would do it is I would do 16. When I say divided by 26, one thing you could do, just quicker, is I'm going to say multiply times 26, and I'm going to hit the x to the -1 power. Now, 16 times 26 to the -1 power means 16 divided by 26, right? Then I'm going to do subtract. And this will work because order of operations exponents are done first. So 16 divided by 26 minus 7 divided by 26. I'm going to do the same thing. 7 times 26 to the -1 power. Hit the x to the -1 button. So there's my test statistic, all right? So this is difference of proportions. And by the way, I'm going to subtract 0 here, right? I'm going to subtract 0. So I don't even need to say -0. I know it's going to be divided by, I'm going to say -0. So it's just this thing, -0. So I'm going to leave -0 out. And I'm going to divide by the standard error, which is 0.138. This is the test statistic. That's what it is. And I'm going to hit enter. I'm going to store this in alpha A. Okay. And I believe in this particular problem, we want to see if there's any difference between the two. This is a two-tail test, I believe, right? Two-tail. So this is where we're going to multiply 2 times the p-value. Excuse me, to get the p-value, it's 2 times an area. The alternative hypothesis says not equal to. So it's going to be 2 times, and then we have to use normal CDF. Now, all right. Now, the difference, these test statistic is positive. We got something that was positive. So the area that we're finding is to the right, because it's a positive z. Remember, the mean is 0 for standard normal. So positive z means we're going to find the area to the right, the tail. And therefore, we're going to use A as our lower end and 1,000 is our upper end, all right? Because it's a right tail that we're finding the area. And so it's already set up that way. Now it's 2 times that because it's a two-tail test. And there is our p-value, 0.0121. So are we going to reject the null or not reject the null? But I believe the problem said we had a 5% significance level. This p-value is less than 5%, less than 0.05. Therefore, we would reject the null hypothesis. We would say at the 5% significance level, we have enough evidence to support the claim that reliable behavior leads to dogs making better decisions in choosing cookies or whatever dog bones, whatever they were getting. All right. So the alternative hypothesis, there's evidence that support the alternative hypothesis. Any questions about that?
I have a question.
Yes, go ahead.
So I have 2 actually. So if our p-value was over 0.05, then we would accept the null.
All right, we never say accept the null. We would say do not reject the alternative, do not reject the null.
Okay.
It doesn't, I think I mentioned before, but I'll say it again and many times, is that we never say, if there's not enough evidence, we would never say accept the null. We would say do not reject the null. Because it's still possible that the null is still false. It's possible. Now, why would we not reject? If alpha in this case was less than the p-value, all right? If the p-value, in other words, was greater than alpha. For example, instead of a 5% significance level, let's say alpha was 0.01. 0.012 is larger than 0.01. And that would have been a case where we would not reject the null hypothesis. So the two choices are reject the null hypothesis when the p-value is less than alpha, or do not reject the null hypothesis. There's not enough evidence to reject it. Okay? If the p-value is greater than alpha. Does that
Okay.
make sense? Make
Yeah.
sense? Yeah. Okay, good. That's a
My
good
other
question. I'm sorry,
um,
did you have something else to say?
Yeah, I have another question. So if the z-score, or if the z was negative, then we would do like the upper, or the we would do the
Yes, good question.
upper
Good
for
question. It's a good question. This is a two-tailed test. Now, when we actually calculate the z, right, it's either going to be positive or negative, right? In this case, it was positive. So if it was negative, let's say we ended up with a negative z, we would do a left tail calculation, all right? And then multiply it by 2, because it's a two-tailed test. So the left tail calculation would be normal CDF, where we would put negative 1,000 as the lower end, and the upper end of the interval would have been A. In this case, that's where we're storing our test statistic. That's a very good question. If we have a two-tailed test, we would, and we had a negative Z, we calc that area is the left tail.
Okay, thank you.
Yeah.
Could you re-explain the last part of that, of the question you just asked?
Yeah, his question was, say in this case here, the Z is positive. Since it's a positive Z, that means that if we drew the standard normal curve, it's to the right of 0, right? So it's the right tail.
Okay.
So we're going to calculate the right tail area, right? And then multiply it by 2, because it's a two-tailed test. His question was, what if the test statistic is negative, right? Well, that's to the left of 0. That's on the left end of the curve. We would do normal CDS as if we were calculating a left tail calculation, and then multiply that by 2.
Okay, thank you.
Yeah, very good question. Thank you for those questions. So I'm going to stop sharing now. That's basically how we do it. I think we showed you an example of a left tail alternative hypothesis where it was less than. But the book goes through this, and then you'll see for chapter 6, I give examples of left tail also when we get into chapter 6. Now, chapter 6, by the way, everything's the same as what we just did here, with a couple of exceptions. The first exception is, let me stop sharing here. The first exception is that the standard error in the test statistic calculation is no longer going to be off of stat key. It's going to be calculated, all right? So you have to calculate, and I'll show you in the videos, you'll see how it's done. But that'll be part of the formula. You just plug in a number for the standard error, you actually calculate it. But it's done as part of the test statistic. And again, you'll see in the video exactly how I do it, all right? It's very clear in the video. So we're not even going to use stat key at all when we're calculating the test statistic, all right? So that's what's different about chapter 6. Also, what's different about chapter 6 is that when we have a hypothesis test for a mean, there's going to be an assumption, which we haven't talked about yet, about the standard deviation of the population. And it's going to, and we talked about this we haven't talked about it yet, but it'll be talked about in those videos. That's why the videos are very important, because if the standard deviation of the population, and this is only for when we have a hypothesis test for a mean, when the standard deviation of the population is unknown, then what we replace the population standard deviation, we replace it with the sample standard deviation for that one sample that we got. So that'll become clear. That's why you have to watch the videos, because when we do that, we're no longer going to be using normal CDF to find the areas. We're going to use what's called T-CDF. And again, it'll be explained to you in the videos. Now, when we do confidence intervals in chapter 6, what's required is for those of you who have 83 calculators and did not come up to me with your calculator and to have your calculator updated, is it's required that you watch a video. Unfortunately, you have to do this on your own, but this is the way I did it. It's not a big deal. It'll just have to take some time. So let me show you where you find this on the internet. It's not hard to find. What you need for your 83 calculator is inverse T. Now, where you find normal CDS and inverse normal and all that stuff, people with the 83 calculators, you will not find inverse T, INVT. So what you have to do is program it into your calculator. There's just a few steps. And I found here a YouTube video, right? So basically, to find this, you would type into your browser type into Google, calculate or program. You write something like this: program inverse T, INVT, for TI-83 calculator, something like that. And then what will pop up is one of these videos. So this is an example of it. It says programming INVT into an 83 or 83 plus calculator. And there's a video and an audio. You can hear them step by step. And what you're going to do is actually follow the steps with your calculator. And if for some reason, and I've had people do this and they had no problem. They did it and it worked. But if for some reason you have difficulties with it, when I come back, make sure you bring your 83 calculators with you on December the 1st, and I'll program it. What I'm going to do is just transfer the program from my calculator to yours. But since there's time to do this, you should probably do this and follow the steps. Again, how long will it take you? 15 minutes. Doesn't take very long. All right. So I would recommend doing that and doing it on your own. And if you have any problems with this, any questions that deals with finding confidence intervals for means, to estimate means, then and you need inverse T and you couldn't do this, then I'll just take care of it for you on December the 1st. But I would recommend doing this yourself. I believe I've had other students do it, and it's not a big deal. Right? So that's one thing. And then I know I'm keeping you on a little bit long, but I just want to show you one more thing with the homework. All right. So don't mind staying on just a couple more minutes. Just want to point out something to you. So I don't know if any of you ran into this difficulty with the homework. I believe it's in section 4.3 homework. Can everybody see this? This is Wiley. Can everybody see it? Just yell out, yes, I see it.
Yeah.
Yeah, okay. So this is just my version of Wiley, the instructor. So let's go to 4.3. All right. And all right. I'll just bring it to your attention. Okay. So this is on hypothesis tests. And let me see if I remember where it was. This shows this Jesus here. A lot of these are just like the ones we were looking at. So let me see if I can find ones that the student mentioned to me. Here it is. Oops. All right. Now, in this particular problem, this is a difference in proportions question. All right. And the question is, this is a 2x2 table, and you have to determine what the two proportions are. So let me just read through quickly what this is saying, and then I'll tell you how to calculate the proportions, because it's maybe a little confusing. At first, when I was looking at it, the wording wasn't really clear. All right, so they're referring to an exercise that was done back in chapter 2. It's a study whether frequent use of digital social media by teens is associated with the development of ADHD symptoms. I'm sure you know what that is. Researchers rated the frequency of social media use as high or low. All right, so here it is, high frequency, low frequency. And it says 2 years later, they recorded whether or not ADHD symptoms have been diagnosed for those people, for those students. And this is the result here. All right, and they're saying you have to test whether the proportion of teens being diagnosed with ADHD is higher for teens with higher frequency of social media use than for those with lower frequency of social media use. So what are the sample proportions here? So it could be a little confusing. So the high frequency social media use, how do you find that proportion? Well, it's the high frequency group that we're looking at, okay? High frequency, this is that line here. There's 165 students who were in the high frequency group. How many developed ADHD out of the 165? 16. So the sample proportion here is 16 divided by 165. All right? It's not 16 divided by 39. It's 16 divided by 165. That's the proportion for the high frequency group. And then the low frequency group, the proportion is 23 divided by 495. It's not 23 divided by 39. All right? So the difference in proportions would be 16 divided by 165 minus 23 divided by 495. So I wanted to bring that to your attention so that you know exactly what's being tested here. All right? Those are the two groups. The high frequency group is group 1. The low frequency group is in group 2. And the number of students who are in the high frequency group is 165. The number of students in the low frequency group is 495. Those are the sample sizes for the two groups. Any questions about that? Because again, it's a little confusing the way they worded it here, and I just want to make it clear on how to do this problem. All right, and then one other thing I wanted, let me see if I can find it. If I can't find it here, then I will just answer questions when they pop up. Let me see if I can find it. I'm not sure where it is, but not even sure whether it's in this section or not, but I think it is. All right, it's not here. All right, so don't worry about that other one. You may have questions about it later, and you can always send me an email. Now, you can always send me emails. My schedule, it might be difficult to get back to you right away, but I will certainly try to get back to you within a couple days or so. So most likely it'll be at night as opposed to normally during the day. So if you have any questions about homework or anything, just send me an email and I'll try to get back to you as soon as I can. Any questions? Anything else? I hope this was good. I hope you learned something from today, and very highly recommend that you read the book. You can listen to this video again. This video, by the way, this recording will be posted tonight, and you'll be able to see it again if you'd like to see the video again. All right, you can always pause it and things like that. Any questions? All right, well, Seth, thank you for staying on, and I'll stop the recording now. And then remember, starting on Wednesday, you'll watch these recordings on your own, pre-recorded recordings. I've set everything up through week 14. All right. So this week is week 12, week 13, week 14. All right. So you just follow it in Canvas. Any questions? Okay. And I will see you guys on December 1st.